Hello all. We got a long question ahead of us, but one that brings us back to results from chapter 11 and this concept of the self force and that radiation reaction, things of that nature. It's not leaving us, and there's so much more to talk about on it. So for this one, it is going to illustrate a pretty cool concept, but man, is it a mess. If you're going to do this problem, I highly recommend, I have here in my notes, to use something like Mathematica to help you, because it will drag you down as far as the algebra is concerned. But nonetheless, let's go ahead and look at what we got. The statement reads, an electric dipole consists of 2 point charges, plus or minus q, each of mass m, fixed at the ends of a, quote, massless rod of length d. Do not assume d is small. A, find the net self-force on the dipole when it undergoes hyperbolic motion along a line perpendicular to its axis. B, notice that this self-force is constant, i.e. t drops out, and points in the direction of motion, just right to produce hyperbolic motion. Thus, it is possible for the dipole to undergo self-sustaining accelerated motion with no external force at all. Wow. Determine the self-sustaining force F in terms of M, Q, and D. Word of warning, there were several footnotes on this question that I'll have to put in the description. But even as you can just probably read from this is going to be a little involved, so let's draw it out. All right, so we were told we had an electric dipole, plus Q minus Q, separated by a length D. Again, so that tells us that we're perpendicular to the axis, so let's orient it to where we have D over 2 above and below. And now what we have to understand here is that the communication of one particle to the next is going to happen at some later time, because this particle gives off its location and the positive Q will receive it here. So we're going to have to take into account things like the retarded time. And that being said, this is why we have a script R, and L tells us the separation there. So remember everything that we had to deal with in chapter 10 and 11? It's coming back, and let's see it put to use. All right, so our solution, well, in part A, under hyperbolic motion, we know what the x of t looks like. It's c over alpha times the square root of 1 plus alpha t squared minus 1, where alpha was equal to f over mc. The force of plus q on minus q will be the mirror image of the force on minus q on plus q in the x-axis, and the net force in the x direction, the net also the net magnetic force is 0. So all we have is all we need is the x component of E. At positive q due to negative q, this is E equal, of course, if we have a point charge moving, we have to use the formula here. Again, this is from chapter 10. So here we were able to describe everything on the diagram, but now we need to write it out formally. U being c script r minus v. This tells us that the x direction is equal to c. Script r was L over script r as far as magnitude. And then we have minus v, and then we factor out the 1 over r, the magnitude of 1 over r by putting it in there. Then script r vector dot u leaves us with a cr minus lv, and then script r dot a leaves us with an la, again for the x direction. So let's tidy up this electric field. All right, so we see that Ex, once we plug everything into this formula, we have negative q over 4 pi epsilon naught script r over c script r minus lv cubed. Then we have, of course, the u there that we have for the x direction, dotted or multiplied with c squared minus v squared. Then we have the other products there that we need to account for. So we have a lot going on, and we need to simplify this beast down before anything else can be done. Notice here that we can factor an A out of sorts and start canceling things here in these two situations, VL and LV. This one we just kind of multiply down so we can get rid of this bracket here. And then we're still left with a 1 over R. So once we cancel that down, and we're left with CL squared minus CR, we can kind of force these factorings to cancel by distributing this R into this one. So cancel that one after we force factored on this script R. Here we had 1 over script R, and we only had a factored 1 here, so we double that, or rather we multiply it by 1 so we could factor it out. Again, these factoring techniques, nothing new, but we're just trying to cancel away what we can. Okay, so as you see, the evolution of trying to simplify this thing continues. But we see here that L squared minus R squared gives us a negative D squared via the Pythagorean relation. So we have that, and we're good there. So without further ado, we see that the force on positive Q is QEX, and there's an equal force on negative Q. So the net force on the dipole, we're going to have to multiply it by 2. So we see that we get a 2 there, and negative Q times positive Q gives us negative. So that's where the negative 2 is. And of course, the same magnitude of charge, so it's squared. And of course, over everything else, and we see it kind of simplify down to this. Now that we have the force, we can see what it means for the hyperbolic motion. All right, so it still remains to determine R, T, V, and A and plug these in. So we know that V of t is equal to dx dt, and so if we know from hyperbolic motion that formula of x, take its derivative, cancel it down, we see what we have, and this comes out to a c alpha t over the square root of 1 plus alpha t squared. We need to evaluate to set the retarded time now, and that's where we see this nonsense here. And I say nonsense because now we're subbing in a big T due to this square root term. It's not going to leave us alone. And the retarded time, as you know, does prove difficult in these setups. So we'll have to be very careful of that. Similarly here, A at TR is just dV by dTr. So we take the derivative of this with respect to TR. And so pushing that through, we see that we get C alpha over T cubed, kind of expected in this kind of situation here. That being said, be very careful with the algebra and simplification of the calculus. But again, this leads us to the question of what is TR. So now we have to go back to chapter 10, sub in everything we found out from the retarded distance as a function of the retarded time. So we get c squared multiplied by t minus tr squared is equal to the script r squared, the retarded distance, or the function. But we know that script r squared is equal to L squared plus D squared, which is what we had in the diagram. So let's be aware of that and be careful. And when we do this, we see that L was defined as x of t minus the xtr. So here is where we're going to be careful and get a headache of a mess coming through. Clearly, if we square this parentheses here, we end up with this. It's just a FOIL situation. Here, if we want L squared plus D squared, we're going to have to square this bracket term here and add it with the D squared. So squaring this bracket term gives us the first square root, the second square root, and then a minus of the cross terms here. So be careful of that and let it simplify down. If we divide both sides, the c squared off of both sides, we can simplify, of course. That's what we see here. So we can uncover the t minus 2t tr plus tr squared. And we can kind of simplify down what we got going on inside. We have a 1 plus 1 that gives us 2. And, we're just stuck with this until further simplification. As you see, a tool like Mathematica could help with this. So use accordingly. So as we continue our simplifications, again, all of this was shown to be incredibly tedious in chapters 10 and 11, dealing with the retarded time. Nothing's changed here. Make our back substitution of alpha in there, and we see that we can clean up as much as possible. We see we had a nice little cancellation of some of these terms, and we're still, quite frankly, we're left with a lot of other work to do. So I'll just let you read through the algebra a little bit here, but we're seeing that by doing it, we're trying to uncover t's here to cancel and cancel the tr's on both sides, thus leaving us with just a tr here. If we want to isolate the retarded time, we have to put all the factors of the retarded time on one side and clean up on the other side. Again, each step of this makes a more difficult mess to deal with. So if you used a program like Mathematica, again, to solve for TR, it would already produce something for you. So I'm just going to let you read through the algebra here. But as you can tell, each successive step in trying to isolate TR turned out to be more rigorous and more tedious. Go ahead and pause the video here to read more of it if you want it. I'm going to move on. All right, so finally we end up with something like this with all the substitutions, all the types of simplifications we could do to this form here, where we have t squared plus tr squared minus 2tr minus t times tr with this and all this other stuff equaling to 0. At this point, we could solve for tr in terms of t, but since v and a are already expressed in terms of tr, it is simpler to solve for t in terms of tr and express everything in terms of tr. So let's go ahead and do that. Again, more math, more math, more math. Simplify, simplify, simplify. Keep in mind that this thing here turned into this after we factored everything. Factor down. All the free terms are over here, and this is equal over here. So we could factor out a t from these two terms, push this bracket over to the 0 side, which is what we do, and then take the square root. As you see, this grossness comes about, so be careful. Like I said, let the algebra do its work. Just be careful on the cleanup because, as you see, it is not easy at all. So let's move forward. All right, finally, we get something more manageable where we're still left with this plus or minus thing on a square root. And what sign? Well, for small alpha, we want t to be approximately tr plus d over c, so we need the plus sign. Again, these kind of things that we see, that assumption of what sign, that's where we need to know the physics. The rest of what we just did was a bunch of algebra, calculus. That was more of just a pure math of simplifying. But to answer questions like what sign do we need, that is the physics part, and that's the hard part. Clearly, we're going to be left with this tag along term. So in this expansion, we'll just let that be capital D. And so we can finally clean up things as much as possible to the point where we see that we have this little expression, quote little, and so we can finally answer things like script r is equal to c times t minus tr, plug the things in for script r, and now we can go back to the start equation and solve for everything. Again, more of these solving steps, plug it in, square up, move away what you need to, isolate t, or in this case L, move it through carefully. Please be careful, please be careful. It is a mess, a gigantic mess, and it requires a lot of tedious bookkeeping. All right. So coming down to the closing point then, after we tidy this up, we see we had a nice cancellation here, of course. Then we're left with AD times D over 2C times T. We solved that earlier, or substituted that in earlier. Just substituted in the capital D. Okay, holy moly, what a gigantic mess of trying to define everything in this blessed question. and this equation. Let's see what it boils down to. Now that we have everything to plug into the force, let's go ahead and do so. We notice that when we're subbing in for the bracket, we had a cancellation of the negative signs and the 2's. Wonderful. Now we still see that we have this disgusting cubic term here, which gets its own bracket joining together with the t. And if we back sub on what the t is, then we could put dc capital D in there whenever we multiply by CR minus LV in the cubic term. That simplifies down. Then once we cube it, we see that we had a nice cancellation of a lot of stuff here in the numerator. So we're left with an alpha over this dc times capital D cubed, which we just said a few slides ago was the square root term. And so here we finally can write down a compact form of the force. I hope by now you see that me stating that Mathematica could be used is not an understatement and is heavily advised. And then of course we have alpha being what we saw back in chapter either 10 or 11. I'm not really sure where we first defined it. So that being said, the energy must come from the reservoir of energy stored in the electromagnetic field. That was something we saw back in chapter 8. So now that we have this boxed up form of the force, now we need to go answer part B. So finally then, finally, we have this force here, which is equal to MC alpha. And here, if that's the case, if force is equal to MC alpha in this constant case, and we just solve for the self force, we now need to set them equal to each other so we see that the alphas cancel immediately. Wonderful. And now we see that it's 1/2 due to the force on one end due to the other. So remember that we had a net force to begin with in part A. Now we're looking at the self force, which is one part onto the other, so we're multiplying it by 1/2. That's what that comes from. All right, so now that we're done with all that, now let's go ahead and take this bracket, multiply it over, divide by the MC term. So you see they switch positions. And by doing so, we are trying to tidy up everything that we can. The 1/2 and the 4 give us 8 pi epsilon, and the c squared term that we get here in red, it's reduced down to 𝜇0. So you see we're starting to get to the form of something we saw before. 𝜇0 q squared over 8 pi md, okay, and m being the mass. Now we need to square everything and then take the cube root. So to get this 3/2 power, we multiply or put everything to the 2/3 power, which is what we see here. Okay, so let's not make any mistakes that things are going to get hectic pretty quick. That being said, it's easy to since we have to undo everything, we're going to be very careful with how we algebraically solve this through. But without any further considerations, let's let the algebra work its way down and see what we need to do to cancel this out with all of this. Simplify through, push it through. I don't know what happened here. That may have been a typo, so my apologies there. Yeah, it's a typo. That should be mu, not q squared over 8 pi md. We're just trying to isolate, get rid of this 3/2 using it on this. So it worked well here. I don't know what happened elsewhere outside of us, or outside of, I don't know what happened on the program using overleaf, I suppose. But nonetheless, I think we see that it's self-corrected here and here, so that's just a typo. My apologies. Now we just need to isolate the alpha down, and we see that alpha is equal to the square root, nonsense. And if we saw that we had f equal all of this, and we want to solve in for the alpha that we had, plug it in, because we see that MC is equal to alpha. So if alpha is equal to this, plug it in and simplify it out. That being said, a very tedious question. These questions are still talked about a lot, or rather, these questions are discussed a lot in research papers, and clearly they are highly complex as far as needing to know how to assemble parts of it together, when to use what. So with that, I will link the papers referenced and we could talk about it more. But yeah, use the tools we have. We live in a much different age than the professors who wrote this book. Bless their hearts and their hard work. I don't know how they did it without, going crazy, or maybe they did go crazy. I still appreciate all their work because this stuff is fascinating. But boy, I have a much bigger appreciation for it after doing all these questions with y'all. And this was a lot of fun. And I'll see you at the next rodeo.